Hey guys, how's it going? Me, Ralph here today. So, I have another math problem to share. Yeah, let's get to it. So, suppose we had a line segment of length n. 2 points are chosen on this line segment independently at random. Let's call these points A and B. Oh, handwriting. So the question is, what is the expected value of AB? So this problem, it's actually pretty simple if you know how to do calculus, but now this problem is actually pretty simple if you know how to do calculus, so I would encourage you to look for a non-calculus solution. Yeah, just in case you don't know what expected value means, expected value means you run lots of trials, take the average of all of those trials, and what would you expect as the average? So for example, if you were rolling a six-sided dice, a standard six-sided dice, and you wanted to know the expected value of one roll, well, you would just take lots of trials and take the average of those trials, and what would you expect to be the average? So if you did lots of trials, you would expect 1/6 of the trial to give 1, 1/6 of the trials to get 2, 1/6 of the trials to get 3, and so on for each trial, for each possibility. And if you just took the average, you would expect 3.5 as your average. Because you just added up 3.5. Now, keep in mind that expected value does not mean you expect to get the value, because you would never roll a standard six-sided dice and expect to get 3.5 unless you're high or something. But yeah, expected value just means you take the average of lots of trials and what would you expect to be the average. So yeah. Pause the video now to try to find the non-calculus solution for yourself. And I will give the solution in 3, 2, 1. Okay, so for the expected value of the length of AB, that's A and B are chosen on a line segment of length n, we're going to say the expected value is equal to f of n. So just some function of n. We're going to find properties of f of n, then figure out what f of n is equal to from there. So now we consider two cases. Case 1. Oh, right. I skipped a couple steps. Alright, so also we're going to mark the midpoint of the line segment. Let's call it M. And now we consider two cases. Case 1, A and B are on different sides of M. And case 2, A and B are on the same side of M. Just note that these two cases are equally likely. Here's a proof. So you choose A, it's on one side of M, and the probability that B is on the other side is 1/2, because this is the midpoint, so it's the other side would be half of the entire thing. And then if B is chosen on the same side, it's also half of the entire thing. So geometric probability of each case is 1/2. They're equally likely. As a result, we can say that the expected value of AB is just the average of the expected value in each case. So is equal to 1/2 expected value of case 1 plus 1/2 expected value of case 2. So let's consider these cases individually. For case 1, we can, since they're on opposite sides of M, we can just say that AB, length of AB, equals AM plus MB. The length of AM plus the length of MB. So in this case, the expected value for the length of AB is the expected value of AM plus the expected value of MB. So what is the expected value for AM? Well, I know that A is chosen on half of the is A is being chosen on a line segment of length half n, and one of the endpoints is m. So, as a result, like, let's put it this way: A is being chosen on this half, and m is the one of the endpoints of this line segment here. So that means the length AM can be anything from 0 to half n, because it would be 0 if, it would be 0 if A landed exactly on M, and it would be 1/2 n if A landed on the other endpoint. And you would expect this to average out to 1/4 n. Because A can be anything from 0 to 1/2 n with equal probability because it's being chosen randomly. And we can use the same argument for MB to get that this would also, the expected value for MB is also 1/4 n. So if we just add those up, 1/4 n plus 1/4 n equals 1/2 n for case 1. That's the expected value for case 1. For case 2, A and B are being chosen on the same side of M. So let's just say it's being chosen on the left side. Well, A and B are being chosen independently at random on a line segment of length half of n, which means the expected value of AB in this case would just be f of 1/2 n, because that's how we define f of n. So substituting these values for expected value back into this equation, we get f of n is equal to half times half n plus half f 1/2 n. So f of n equals 1/4 n plus half of f of 1/2 n. And now we have a property of f of n that we can work with. So let me rewrite that. F of n equals 1/2, wait, not 1/2, sorry, 1/4. 1/4 n plus half f 1/2 n. Yeah. So now, from here, we should probably try to find an expression for f of 1/2 n. We can do that by substituting n with 1/2 of n into this equation. So that means f 1/2 n equals 1/4 1/2 n plus half f 1/2 of 1/2 n, which simplifies to 1/8 n plus half f of 1/4 n. So now you can substitute this this expression for f of 1/2 n into here. So we would get f of n equals 1/4 n plus 1/16 n plus 1/4 f 1/4 n after simplification. So now we need an expression for f of 1/4 n to substitute back in here. We can substitute 1/4 n for n in this equation to get an expression for f of 1/4 n. So we get f 1/4 n equals 1/4 n, this here, plus 1/2 f 1/2 of 1/4 n, which simplifies to 1/16 n plus 1/2 1/8 n. That's not correct. 1/2 f of 1/8 n. So now we have an expression for f of 1/4 n, which can be substituted back into this equation we can substitute that back in here. So we get fn equals 1/4 n plus 1/16 n plus 1/4 times this expression. So 1/4 times 1/16 is 1/64 n. 1/4 1/2, so 1/8 f 1/8 n. And now we need an expression for f of 1/8 n. and then we would do basically the exact same thing, substitute 1/8 in here, get an expression, put that in here, and repeat, and repeat, and repeat. And you'll find that eventually you'll get f of n equals 1/4 n plus 1/16 n plus 1/64 n plus, what's next? 1/256 n plus so on. You would get a geometric series here plus 1 over some really large power of 2, ln for large number, large power of 2, f of 1 over the same really large power of 2, n. Here I'm just going to use ln to substitute for some really large number. We would eventually get that if you did it a large number of times. And if you take the limit as you as you do it infinitely many times, you would get f of n is 1/4 n plus 1/16 n plus 1/64 n plus so on. You would get an infinite geometric series here, plus, and then this would just go to 0 as the large number gets larger and larger. This would just go to 0. So plus 0, or we can just ignore the plus 0 because that doesn't do anything. So we would get an infinite geometric series. Now to prove that rigorously, it's not too hard, but it just takes a lot of time, so I'll let you do that yourself. Then we just need to evaluate this infinite geometric series for f of n. And yeah, I just hope you were paying attention in Algebra 1, because yeah. Or even if you weren't, I hope you know how to do this, because I'm really bad at explaining something like this. 1/16 n plus 1/60 n plus equals 1/4 n over 1 minus 1/4. Because you just use the formula for the sum of an infinite geometric series. 1/4 is the common ratio, as you can tell, and the first term is 1/4 n. So that simplifies to 1/3 n. And yay, we have our answer. F of n is equal to 1/3 n. That's how I would do it without calculus. So what can we learn from doing this problem? Well, mainly, what I got from this problem is that you should sometimes write what you're looking for as a function of some variables, figure out a property or properties of that function, then solve for the function from there. That can be used to solve a couple of problems. That's mainly what I learned from this. Also, don't be afraid to do a lot of work. Don't be afraid to take stuff as it goes to infinity, because that's basically what we did here. We just imagine we did it an infinite number of times, so that eventually this term would just become 0. So we got an infinite series, which was pretty easy to evaluate because it was a geometric series. Alright, that's the non-calculus solution. So in case you were wondering how I could do this really simply with calculus, I'll just present the calculus solution now. So the problem is we have a line segment, length n, and 2 points are chosen on it independently at random. Well, instead of thinking of it as a line segment, we can think of it as a section of a number line, with one endpoint corresponding to 0, the other endpoint corresponding to n. And we know that the length of this segment of a number line is equal to n because one endpoint is n, one endpoint is 0, n minus 0 is n, so distance n. 2 points are chosen on this segment of a number line independently at random. So we can just they would just correspond to numbers on the number line. We'll call the numbers a and b, so let's call this a, let's call this b. Then if you know how number lines work, you'll know that the length AB is equal to the absolute value of a minus b. Since we're basically running a lot of trials and taking the average, we need the average value as both a and b vary. So first let's imagine how we would calculate it if a is constant. So a is constant. It's not actually constant, we're going to pretend it's constant for a moment. Then the average value, or, well, expected value as well, but the average value for the length of AB, or just absolute value A minus B, would be 1 over n integral 0 to n of absolute A minus B dB. Because, average value formula. So then, A is not actually constant, so we also need to apply the average value formula with respect to A. So that would give us 1 over n integral 0 to n of 1 over n integral 0 to n of absolute A minus B dB dA. And that would just be our expression for the expected value of the length of AB. Because in this case, expected value and average value mean the same thing. By definition. So this might be a little bit gnarly to evaluate because of the absolute value of A minus B in the middle here. But that can be you can get rid of that absolute value by simply noting that integral 0 to n absolute A minus B dB equals integral 0 to A of A minus B, that's correct, dB plus integral A to n of B minus A dB. This expression can be rewritten as these two integrals because of the definition of the absolute value. So then you would just take this expression, put it back in here. That would look like not good. A minus B dB plus integral to n of B minus A dB dA. That would just look like this. Now that's a lot of numbers and letters. Well, just letters, but evaluating this isn't actually that hard if you know how to do it. So I'll just let you do it yourself because it takes some time to do and it's not too hard anyway. And if you do it, you'll eventually end up with 1/3 n as the answer. So the calculus solution agrees with the non-calculus solution, or at least my non-calculus solution. So yeah, that's it for today. Thank you for watching. Please like, comment, and subscribe. If you're still confused about some steps of the solution, or if you want to ask about some steps that I may have skipped, please don't hesitate to ask in the comments below, or contact me if you don't want to get a shaming for being confused about something that other people might think is easy. So if you don't feel comfortable asking in the comments, just contact me. My contact info will be in the description below. And thanks for watching. See you next time.